Hi everyone, thanks for your interest in our paper. This is Jeonghyeok and Munchurl Kim. We are glad to present our work, SkateFormer, Skeletal-Temporal Transformer for Human Action Recognition. Human action recognition often uses RGB videos for classifying actions, but they are sensitive to lighting, camera angles, and require large storage. 3D skeletons from sensors offer a compact and robust representation, unaffected by environmental changes, unlike RGB inputs. Graph convolutional networks, GCNs, struggle to capture long-range joint interactions and temporal dynamics effectively. Transformer-based models can capture relations between all joints using self-attention, but may suffer from inefficiency and can obscure key skeletal-temporal relations. Recent research explores transformer-based approaches for skeleton-based action recognition. However, these methods often require high computational costs due to the usage of their large-sized attention maps. Considering every joint in every frame is inefficient, as specific joints in certain frames are more critical for particular action recognition. To overcome these issues, we propose an efficient transformer-based approach called Skeletal-Temporal Transformer, SkateFormer. We introduces joint and frame partition strategies and partition-specific self-attention based on types of skeletal-temporal relations. To make our SkateFormer computationally efficient, we introduce a novel partition-specific attention, SkateMSA. For this, we divide the skeletal-temporal relations into 4 partition types based on 2 skeletal relations and 2 temporal relations. For example, in the Make OK Sign action class, relations between physically neighboring joints, such as joints on the same hand, are crucial, whereas in the Clap action class, relations between physically distant joints, such as between the palms of both hands, are more critical. Regarding temporal relations, for repetitive local motions like in the brush teeth class, neighboring frame relations are essential, whereas for actions with global motion like sit down, distant frame relations become critical. Additionally, the speed at which actions are performed can vary significantly depending on the actor. This is the overall architecture of our proposed SkateFormer. First, the 3 linear layers in the SkateFormer map the low-dimensional raw skeleton data into a higher-dimensional feature space. We then perform the skeletal-temporal positional embedding by adding learnable skeletal features and fixed temporal index features to this mapped feature. The embedded features pass through SkateFormer blocks, each comprising a self-attention layer that propagates features via skeletal-temporal relations. The final features, after SkateFormer blocks, undergo skeletal-temporal pooling to produce the outcome Y. To make our SkateFormer computationally efficient, we introduce a novel partition-specific attention, SkateMSA. For this, we divide the skeletal-temporal relations into 4 partition types. Neighboring joints and local motion as Skate Type 1. Distant joints and local motion as Skate Type 2. Neighboring joints and global motion as Skate Type 3. And distant joints and global motion as Skate Type 4. Therefore, SkateMSA is designed to efficiently capture skeletal-temporal relations at the joint element level, eliminating the need for tokenization. We partition the joints and frames together into 4 types through a skate-type partition operation P. The partitioned feature map undergoes multi-head self-attention, MSA, and is then reshaped back to its original size through a skate-type reverse operation R. Self-attention is applied among elements of the same color in the feature map. The computational complexity of a naive self-attention layer and our SkateMSA is as follows. In our experimental settings, this results in approximately a 48 times reduction in computational complexity compared to the naive self-attention layer. We present a comprehensive performance comparison for our SkateFormer against recent state-of-the-art skeleton-based action recognition methods. The extensive experiments demonstrate that our SkateFormer outperforms all the state-of-the-art methods except the E4 of X sub 120. It should be noted that the performance of our SkateFormer is relatively higher for E1 and E2 than E4. This is indicative of the SkateFormer's attention strategy, which is based on partition-specific processing, allowing for the simultaneous handling of all inputs within a singular network. This table presents the impact of different skate types on accuracy. As shown, Incorporating the skeletal relation types only improves the action classification performance over the baseline, and so does the temporal relation types only. The full model that utilizes the skate types achieves the highest accuracy. We additionally performed experiments in this table in terms of measured flops and memory usages in perspective of the attention layers only. To analyze the significance of different skate types concerning action labels, we conducted an investigation within SkateMSA. For actions such as sitting down, action label 7, and standing up from a sitting position, action label 8, where the overall motion of the skeleton sequence is pivotal, the feature correlation maps for skate type 3 or skate type 4 exhibited more pronounced activations compared to other skate types. Conversely, for actions that rely heavily on intricate hand movements like reading, action label 10, and writing, action label 11, the feature correlation map for skate type 1 was prominently activated. Through this analysis, we affirm that our proposed partition-specific attention strategy based on skate types operates adaptively according to action labels. Thank you for listening, and please feel free to visit our project page.